of you? You all have page 356. So what is an inverse function? I wrote it on there for you so that you don't have to write definitions. But it's the result of exchanging x and y. That's the definition of an inverse. An inverse's function is to undo the original function. So here's some inverses you already know. Addition and subtraction are inverses of each other. Multiplication and division, square root and square. You should already know that those are opposites. They undo each other. So if you add 3 to both sides or divide by 2 on both sides, 356. Here are some terms that hopefully you remember from the beginning of the year. What is a function? It's a relation in which each x only has one y value. It has to pass the vertical line test. So for example, our friend the parabola, that's a function. I can draw a vertical line anywhere I want, and I should only touch the function once. When you start studying in pre-calculus conics, a circle does not pass the vertical line test. So it's not a function, right? Because I hit the graph twice and it fails the vertical line test. Today we're going to learn something about the horizontal line test. So function and vertical line test, you should already be familiar with those terms. You should also already be familiar with what domain and range are. Those are on your final exam about all the functions that we've studied. Here are the new terms that I just want to introduce you to today. There's not going to be like a big test on inverse functions, but you have to understand at least like one question on the test, how to find an inverse, because logs only exist if exponential functions have inverse functions. So a one-to-one function is a function in which each y can only have one x now. So our friend the parabola is going to fail the horizontal line test. It gets hit twice, so it is not one-to-one. So not 1 to 1. So the important thing there is a parabola doesn't have an inverse. There is an inverse for a quadratic that we restrict the domain, but the whole function itself does not have an inverse. It failed the vertical line test. Can you think of one of the functions we studied this year that would be one-to-one? Quite a few of them are one-to-one. Give me an example of a function. So just a class of a function. Linear, what? Linear is one-to-one, right? Here's my line. So there's my linear function. It passes the vertical line test, and then it also passes the horizontal line test. Give me an example of something else that would fail the horizontal line test. Another function that we studied with transformation rules. It's similar to our friend the parabola. You think exponential is actually one-to-one, right? Exponential is one-to-one. Quadratic is here. What were you going to say, Finn? Absolute value. That's the one I was looking for. Absolute value, not one-to-one. It means that each x, it means that each y has only one x value. The only reason that's important is because then when you switch x and y, it's going to have an inverse. So these y values, let's say this is like 2, 4 and negative 2, 4. See how 4 is the y value? Well, guess what? It's paired with two different x values. Cubic would be one-to-one, right? So that works. One-to-one means that I can't fail the horizontal line test anywhere. So if I draw a horizontal line, I'm never going to hit. Right, so if it wasn't the parent graph, right, if it was a graph like this, then yep, it totally fails the horizontal line test. But the parent function is this curve, and it does not fail. Okay, so it says, so x squared would not have an inverse, that's a function, but we'll talk about how to restrict the domain so it does. So let's do something with inverse functions so you can understand them a little bit better. This should be your next page, right? So I want to show you this notation. See this little -1 exponent? I hate that they use this as the notation for inverses because we just learned what a negative exponent does. What does it do? Yes, and that's not what an inverse function is. So I hate that they use the same notation. We're used to saying that if I have x to the negative sixth, okay, I can write that as 1 over x to the sixth. That is not what this notation means. This notation just means inverse function. So don't confuse the two negative exponents. If you're simplifying, this is what you do. This just means inverse. So you're not doing the reciprocal. So inverse does not mean reciprocal. They're not the same thing. This is reciprocal. Flip it over. Inverse is switching x and y. So you take a comma b and you make it b comma a. So you switch x and y. That's the big idea for inverses, switching x and y. I don't think we're really going to talk much about the test for inverses, but you plug one function into the other function. Inverses will be a mirror image over the line y equals x. I'll show you that when we do the graphs. And if we're switching x and y, domain and range flip-flop. So domain of the inverse is the original range. Range of the inverse is the original domain because you're switching x and y. So it's a lot of reading, but I think once you see how to find an inverse, it'll seem fairly straightforward. So we're going to find an inverse 3 different ways: using coordinates, using a graph, and then algebraically. Algebraically is where we really want to go here. So using a set of points, this is just a scatter plot. It says find the inverse and determine if the inverse is a function or not. What's the definition of a function? Each x has only one y value. All right, 2 comma 4 is just going to become 4 comma 2. I just found the inverse. All I did was switch x and y. 4 comma 5 is going to become 5 comma 4. 3 comma 8 is going to become 8 comma 3. Done. I found the inverse. Is it a function, and how do you know? Each x can't be repeated. So each x only has one y. I have 4, 5, 8. No repeats. So yes, this is a function. If this is a function, then the original function must have been 1 to 1. Look at the y values: 4, 5, and 8. There's no repeated y values in the original, so there's no repeated x values in the inverse function. I might not have given you enough room. So let's find the inverse of part B. 1 comma 0, 3 comma 2, 1 comma 3, negative 2 comma 4. See how there's no reciprocal going on? You're literally switching x and y. You're not flipping them over. Would you? Not a function. How come? Yeah, 1, 3, and 1, 0. So therefore, the original function was not 1 to 1, right? It was a function, 0, 2, 3, and 4. So it was a function originally, but it was not 1 to 1 because there were 2 y values originally that were 1. So when I flip it, I've got a repeated x value. All right, and if all the points have the same x, y values, the inverse will stay on those exact same points. And yes, this is still a function. I don't have any repeated x values for my inverse. So that's switching the points. We're going to kind of apply what we just did to graphs because we're going to switch points on a graph now. And this is a good review of graphing for your final exam. So it says graph the function, then graph its inverse, and graph the line y equals x. Because, where did I see that? Inverses are mirror images over the line y equals x. So I'm going to graph that line with like a highlighter at the end, just so you can see where the mirror is. What type of function is this? 2x minus 3. Linear. So you start at the y-intercept of negative 3. Next week, we're going to be doing some review work on final exam stuff. So graphing a line, that was our whole first unit. systems of equations, intersection points. 2x minus 3, my slope is 2, up 2 over 1. You want to graph at least 3 points on your original function so that you know how to graph your inverse. There's my original function. I'm just going to write f of x. So how do I find the inverse? I'm going to record those 3 coordinates. So this is 2, 1. This is 1, negative 1. 0, negative 3. Would you agree? Those are those 3 coordinates. How do I find the inverse? I'm just going to flip those coordinates around. I think I'm going to do this in another color just so you can see here. So I'm going to graph 1, 2, negative 1, 1, and negative 3, 0 in red. And this is going to be my inverse function. 1, 2, negative 1, 1, negative 3, 0. I want you to kind of observe how these two graphs are related. So I just graphed the original and the inverse. And then the line y equals x goes through the origin and it has a slope of up 1 over 1. So if you want to leave y equals x like dotted or something, just so you know, one is the original function, one is the inverse. Here's the mirror image. See how it's been reflected over that line? What do you notice about the slope of the inverse function? What's the slope of the inverse function? It's positive. And what is its exact slope? 1/2. 2 and 1/2 are related to each other. The domain of these both happens to be all real numbers because they're both lines. So when they flip-flop, they're still both all real numbers. And can anyone tell me the equation of the red line? What's the equation of the inverse? If I was going to write it using slope-intercept form. What's the slope? You just said 1/2. Yep, y equals 1/2 x. What's the y-intercept? That's the original y-intercept. I'm looking for the red y-intercept. If the slope is 1/2, that has to be 1.5 right there, right? Are you with me? That's 1.5 on the y-axis. So I just figured out the equation of the inverse graphically. It was a long process, but I figured it out graphically. Algebraically is going to save you so much time. So I'm showing you what it looks like when you're graphing it, but you'll appreciate algebraically. All right, see if you can do part B. So see if you can graph the function, go through those steps. Graph the function, find the 3 points, flip-flop them all, graph them, and find the equation the best you can. And I'm going to do the same, and then I'll project it in a minute. Record here so that they can see what I got. This should look about what you got. Did you get the equation right? That it'd be a slope of 3, and the y-intercept is exactly at -3 this time. So that's finding inverse with linear functions, and we're going to take a look at a couple other functions, quadratic, exponential. They all have inverses. Some of them have to be restricted because they fail the horizontal line test. Cubed graph. So this is a good review of parent functions. We haven't used the cubic function very much this year. So I'm just going to remind you of the few key points. What is 0 cubed? 0 times 0 times 0 is still 0, right? So 0, 0 is the first key point. What is 1 cubed? And 2 cubed wouldn't fit, but 2 cubed would be 8. What is -1 cubed? -1 times -1 times -1 is -1. And -2 cubed is -8. So it's this, it almost looks like a tangent graph, those of you in trig, but it doesn't have any asymptotes. So those are the 3 key points of the parent cubic function. So on your final exam, you might have to transform it up or down using the transformation rules that you know. So now I'm going to flip those points. Well, when I flip those 3 points, they don't move. 1, 1, 0, 0, -1, -1 are still going to be right in that same spot. The reason I told you 2, 8, what's 2, 8 going to become? 8, 2. So the cube root function ends up looking like this, and it goes way over to 8, 2 and way over to -8, -2. So the cube root function goes in this direction. It just happens to go through those 3 same key points. But remember, it has to be reflection over the line y equals x, if I draw that in light blue. Cubic functions, what's their domain and range? Any restrictions? I can cube anything I want, right? And I get negative numbers and I get positive numbers. So everything ends up being all real numbers again. And this is the cube root function. So cube root graph. Like the cube root of 27 is 3, or the cube root of 1,000 is 10. All right, x squared. Good review of the parent function x squared. What are some key points? 0, 0 is the vertex. 1 and -1, if you square those, you get +1. 2 and -2, if you square those, you get 4. 1, 2, 3, 4. 1, 2, 3, 4. So like we said, this fails the horizontal line test. So they didn't want to say, oh, doesn't have an inverse. What you're going to do is restrict your graph to only the first quadrant here. So for the sake of, see how it says restrict it so it has an inverse? For the sake of inverses, we're just going to show that we're going to remove that part of the graph, and we're only going to find the inverse of this side of the graph, and that's going to be your square root function. So the inverse is the square root of x, and that has key points at square root of 0 is 0, square root of 1, and square root of 4 is 2. 1, 2, 3, 4, 2. So we just reviewed like 4 of the parent functions, cubic and cube root, x squared, and the square root of x. Let's write the domain and range of the restriction, because I don't want you to get confused. Normally a parabola is all real numbers for the domain. We're just writing the restriction down here. X has to be greater than or equal to 0. And it makes my range y is greater than or equal to 0. And then we get the same thing when we flip-flop it. X has to be greater than or equal to 0. Y has to be greater than or equal to 0. I'm not going to test you on this function and, oh, now we're going to restrict the domain. I'm probably just going to test you on graph a line, graph its inverse, and then graph an exponential function and graph its inverse. I'm going to show you that on the back page. Okay, last but not least, remember I said I was going to show you algebra and how it's faster to find the inverse algebraically than on a graph, and then we'll take a little break. To find the inverse using algebra, remember that the whole definition of inverse is to switch x and y. That's what you're going to do algebraically. But in order to switch x and y, you need to rewrite f of x as y equals so that you have a y to switch. So I just kind of write over the f of x. That's my y. When I switch x and y, I literally mean switch x and y in the equation. So now I have x equals 4y plus 3. I just switched only the x and the y. Everything else stays in the same place. And your last step is to solve for y equals. So your first step is to switch x and y, and then you're going to solve for y. How would I get y by itself in this equation? What do I need to move to the other side? Subtract 3, right? X minus 3 equals 4y then. And then I need to divide everything by 4, right? Divided by 4, divided by 4. What's your final inverse? Y equals, you already said 1/4 x. Right, and then don't forget to also divide your y-intercept, so minus 3/4. So that was easier than graphing the two lines, I think. Okay, so let's do the next one. So this is y equals, so I'm going to switch x equals 3 times y plus 5 divided by 2. There's a couple ways you could go here. You could distribute. I don't like distributing. I'd rather kind of take this shortcut. What would be the first thing? I would multiply both sides by 2 to get it out of the denominator if it were me. So I would just take 2 and multiply the 2 to the other side. So now I have 2x equals 3 times y plus 5. Don't distribute it because you're still going to have to divide by 3 at the end. So I would just divide by 3 at this step personally. That gets rid of the 3. So now you have 2/3 x equals y plus 5. So what's your final equation to solve for y? X, yep, minus 5. Didn't have to graph it. Just use algebra. Because it's a coefficient in front of a factor. So if it had been 3y plus 15 and you distributed it, then see how you're going to divide by 3 and get 5? But the 3 is outside of the parentheses. So because it's outside the parentheses, you only divide it once. All right, this next one, if this is y equals x equals the cube root of y minus 4 plus 1. Yep. So what's your next step on C to get y by itself? Nope. Subtract 1 from both sides. X minus 1 equals the cube root of y minus 4. So remember at the beginning we talked about inverse functions like addition and subtraction, multiplication and division. You're going to cube both sides. You read my mind. I was going to say, what is the inverse of taking the cube root? You're going to cube both sides of the equation. Just be careful that you cube all of x minus 1. You don't want to distribute it. You'd have to FOIL it out 3 times. So we're just going to leave this as x minus 1 cubed equals y minus 4. Don't distribute illegally. You can't just say x cubed minus 1. This is x minus 1 times x minus 1 times x minus 1. So your final answer would be just y equals x minus 1 cubed plus 4 when I move the 4 to the other side, right? I'm just saving the step of adding the 4 and then still rewriting it as y equals. So if you want to write out every step, that's fine. And then on part D, it says you would restrict it so it has an inverse, but algebraically, you do the same thing that we've done in all the other problems. You switch x and y, and then you're just going to take the square root of both sides. So if this is y equals, it's now x equals. So what would be my first step to get y squared by itself? Add 5 to both sides. X plus 5 equals y squared. And then how do I get that y squared? The square root both sides. Yep. So your final answer, y equals the square root of x plus 5. You know how when you take the square root, usually you write plus or minus? In this case, we don't want to write minus because we don't want this part of the graph and this part of the graph. We just want the positive part of that graph. So that's why we don't write plus or minus when we take the square root this one time. All right, so we're going to finish up with a practice of graphing some exponential functions and talking about the inverse graphically. And basically, when you're graphing the inverse, you're graphing a log. You don't know much about logs yet. At the bottom there, we're going to introduce you to what a log function even does to start working with logs next class. So 2 to the x, what are the key points? We know that it has a y-intercept at 0, 1. We know that 2 to the first power is 2. So 1, 2. We know that 2 squared is 4. And what is 2 to the negative first power? 1/2, right? So if I have those key points for my exponential function, I can graph the inverse the same way we did on the front page. So this was 2, 4, 1, 2, 0, 1, negative 1, 1/2. So if you have a cluster of points, you flip the x's and y's, and then whatever you get is going to be the graph of your inverse function. So 4, 2, 2, 1, 1, 0, and 1/2, negative 1 are our inverse coordinates. So wait a minute while you graph those. So it's basically a curve, mirror image over that line y equals x. So it should be what you would expect it would be. What is the original asymptote on the black graph? Y equals 0, right? So if x's and y switch, guess what? The red graph has an asymptote where? At x equals 0. See how it's approaching x equals 0? So I'm not going to draw them in, but x equals 0 is that vertical asymptote. Domain and range would flip-flop, therefore. So let's just do that same exercise with a 3 to the x graph. So why don't you graph your few key points for 3 to the x? You're not going to be able to fit 2, 9, so you can just fit the first 3 points for 3 to the x, and then flip them to graph the inverse, which is going to be the log graph. So what you'll notice is it's almost an identical graph. It's just slightly steeper because instead of over 1 up 2, you went over 1 and up 3. So we're going to talk about these log functions a lot more in pre-calculus, but this is just an introduction like, hey, it has an inverse. Hey, this is what a log function does, which is what we're going to look at down below just to wrap up today. Okay. So can I go down to the bottom and just show you what a log is? So a log is basically an exponential function. So it's just a new way of representing the exponential function. So I'm going to, were you okay with that? Were you done with it? Super? All right. So if you look at the first question, this says log base 5 of 25. So the base is this little guy right here. The base of the log is the base of the exponential function. So if we're trying to evaluate this, what this is asking us, 5 to what power will give me 25? So 5 to what power is 25? 2. So the answer to this log question is 2. The log base 5 of 25 is 2. So if I answered the next question the same way, I'm thinking in my head, 2 to what power will give me 8? So what is the value? 2 to 8, what? It's cubed, right, 3. 2 cubed is 8. So the answer to this log question is 3. You're evaluating that log. So the next one is asking you 6 to what power gives you 6? So the answer would be 1. So the log base 6 of itself is 1. Does that kind of make sense? Let's do one more row together before you jump on trying them. So number 4 is asking you 4 to what power is 16? So what would you say? Squared, yep. And 7 to what power is 49? That one's also squared, right? What about this one? So there's no base written there. So when you are evaluating another type of function, if I was asking you the square root of 16, whoops, what number is really there? No, the square root, right? So in the past, you've seen other functions that like don't put a value in and you already know what value goes there. The same is true of logs. The common log always has a base of 10. So if there's nothing written there, you're going to write in the base of 10 yourself on number 6 and number 14. I think those are the only two. So 10 to what power is 100? The answer would be 2. 10 squared is 100. So I'd like you to take the last couple minutes and try the powers for 7 through 15, and then leave it out because I'll put up the answers in just a minute once you've tried them. Pause my video for a second so that it'll show the answers.